let's get cracking. Like I said, I hope it was like a gentle enough introduction, like, oh, quiz. Not that bad. Let's have a look through. So, sometimes a bit sneaky, right? And this will happen more and more as you go further into the course, particularly when we get to motion. But I just, you have a look at this one. The first question has information you don't need, right? Namely the y-intercept. It's just there. Now, this is really obvious. You all immediately could say, oh, that's there, but I don't really need that. Later on, it will not become so obvious. Like, I have all this information, and sifting out what's important and what is insignificant and won't factor into the question, not as easy as it will look. So just, there you go. You've got your derivative, you pop in x equals 3, and there's your value. When we come here, it's just straightforward quotient rule. Are you happy with that? Is that looking good?
Oh my god, it's quotient rule.
The expanded or the factored form?
Sorry, you're talking about
the denominator.
I need a new color. You're talking about down here, right?
Yes, the preference form.
So the question was, obviously, when you're doing your v, u dash, u, v dash, and then there's your v squared, right? Should I bother expanding out this actual denominator? You can clearly see what I think the answer probably is, okay? Generally, it is better to keep it simplified, keep it factorized, because you gain nothing out of expanding, okay? And in fact, for instance, if I were using this for something else, this means I know that there is one vertical asymptote, right? There's one point where there's a discontinuity in the first derivative, right? If I expand that out, it becomes harder to see that, not easier, okay? So generally speaking, leaving it factorized is fine. You don't gain anything by expanding, and as a bonus, sometimes that's useful to me, knowing where the discontinuities of the function are, okay? Good question. All right, sorry, you may have just slightly ran out of space here to do this equation that's reducible to a quadratic. It's a fairly easy substitution to see. That 4 to the x, how would you rewrite that?
2 squared.
Yeah, so there's kind of 2 steps really. 4 is of course 2 squared, and that's being raised to the power x. But by your index laws, you can see, well, that's 2 to the x squared, which is what's useful to you to make a quadratic, right? Once you've reframed it, lucky for you, these both get solutions, so they're your solutions. Happy? As you come up, possibly one of the most deceptively simple trig identities. But you look at that, and I bet some of you, maybe you didn't put pen to paper, but some of you are like, oh no, which one's the 1 minus x squared thing? So yeah,
somebody who just, there are some people, like when I looked at it, right, I was like, do I make it so that tan is sine on cos or something?
Yeah, it's like, we know a whole bunch of general purpose strategies. Sometimes the most obvious thing is the easiest, okay? By the way, year 12. The dead giveaway clue that you really didn't need to use any form of the Pythagorean identity is just look carefully at how this and this relate to each other. Clearly some cancelling is going to happen, and cancelling is exactly what I'm after, right? The last clue is that tan and cot. Tan and cot, they would go together normally. Like if I saw some different configuration which didn't have the 1 minus something squared, I would just put tan and cot together, which as it happens is exactly what you need. Okay. Alright, lastly, so here's what the, now this is not actually the answer by the way, this is part of the answer, this is probably your working for the answer. We want the intersection, right? We want the intersection, so I'm going to get up now. When you have a look at this, in fact we'll do it this way. When you have a look at this, you have region 1, okay, you're beneath and you can see that it's been plotted as dotted because you're not including the boundary. Then you've got this guy, your absolute value, and you're above because you're greater than or equal to, hence the solid line as well. Now let's actually finish this, right? I want the intersection. That means that both of my regions need to be satisfied simultaneously, okay? So that means you can already rule out like all of this stuff, irrelevant, all of this stuff, irrelevant, all the business is happening in here, okay? So let's start with, there's a point of intersection here, and a point of intersection here. You always start by drawing your points of intersection as hollow, because you can obviously fill them in later, but you can't unfill them. Well, I mean you can, but it's just a bit messy. So I put them in as hollow. Do each of them satisfy both inequalities?
No. But in that case...
Look carefully. Do they satisfy both inequalities? And the answer is no, right? They satisfy the orange one because you've got that solid line going straight through it, okay? But they do not satisfy the purple one. It's right on the purple boundary, which we just said is dotted and is not included. So I leave both of them hollow, okay? Does that make sense? Now I have a look, okay, what's happening in here? There is, and again, I'm going to put it dotted because if I want to fill it in a second, I can. But if I want to unfill it, it's a bit harder. Is that boundary included? Does it satisfy both?
Yes.
It does satisfy both, right? We already established it's on this line, which is a thumbs up, and it's well within this purple region, so I'm going to fill it. Happy times? Okay. Last part, again, boundary. You've got this part of the parabola here. Is it in both?
No.
No, it is not, because it is not in the parabola. So that part is dotted, and now I can actually shade this tiny sliver in here. I'm probably missing one last piece of information. The coordinates of my 2 points, right? So I think my coordinates here are 0, 3, and what is this? 1, 2. Are you happy with that? So it's a very small area. That's what we're after.